Okay, so hi everyone. So in this video, I will be talking quite a bit about what quantum entanglement is and how it works, as well as why it's needed, and how it came to be, like the history of how people actually discovered what it is and how it works. I'll also be talking about how many people tried to prove it wrong, and how many people tried to use this to prove quantum mechanics wrong. So if you guys feel like quantum mechanics or quantum computing or quantum physics, anything like that is pretty new to you and you guys don't know about it, you guys should probably look through my previous videos regarding quantum theory and quantum physics, as well as quantum mechanics. Because I'll be uploading a complete playlist of videos regarding this and to give you guys a better understanding of all it. So yeah. Now let's get into what quantum entanglement is. Okay, so like I said, I'm going to get into quantum entanglement. So quantum entanglement is a pretty complicated concept, and you usually need to know the basics of quantum physics and quantum mechanics to get a better understanding. But an easy way to understand quantum mechanics could be like, you look at one particle over here and another particle over here, and if they're entangled, quantum entangled, what happens is, according to how these particles are configured, let's just say there's arrow on both of them, and we don't know what direction it is, so I didn't put the actual arrow, I just put lines. So let's just say both those particles are spinning. So as soon as I want to check which direction this particle lands on, let's say it's the arrow's pointing upwards for this particle, then according to how this is the other one's configured, we can easily predict that the other one would be pointing in the same direction. And if these are configured in the opposite way, in where they should be pointing in opposite directions, then when the first one's pointing upwards, the other one should be pointing downwards. So this all comes down to how it's configured, but this is one of the basics of quantum entanglement. A more real life day-to-day kind of analogy could be a penny or a coin. Let's say we have a coin here and a coin here, and we quantum entangle these two coins. So what happens is, when you spin this coin, up until you stop the coin from spinning, you won't know whether it's going to be heads or tails. So let's say we stop the first one and we land on heads. Then we know for sure that the second one must land on heads. And the cool feature about quantum entanglement is that the two particles, coins, whatever is quantum entangled, can be separated extremely far away, but the effects would be instantaneous, so you won't see a complete difference. So regarding this, as Einstein calls it, the spooky action from a distance, which is basically quantum entanglement. So Einstein called it this as he was quite against quantum mechanics and quantum physics and stuff like that, because he didn't like the concept of everything that happens in real life not being certain, rather prediction, and you only know the probability of something occurring. So this revolves around superposition. So this is another term I would have explained more deeply in a previous video, but I'll just do a quick warm up on that. So superposition is basically when an object is in motion, or like in case of particle, it's rotating, or it's a coin spinning, and the only thing you can predict is the probability, let's say it's a coin, of it landing on heads or tails. That's the only thing you could find while it's spinning, right? So what happens is, when you'll know for sure is after you stop and actually measure or observe the object. So let's say it landed on heads. So up until the coin stops spinning, you don't know whether it's going to be heads or tails. But as soon as you stop the coin from spinning, it falls on heads. So that's how superposition works. So superposition is basically just tells you the probability of the coin or whatever it is that's quantumized, the probability of it becoming taking one choice or the other. So let's just say in this scenario that the chances, according to how it's spinning, for this to fall on heads is 30%, and tails is 70%. That's about the most you can get out of the superposition and quantum physics. The only time you can be certain of what this actual result will be is after the coin lands. It could be tails or heads. So Einstein, he's a realist, so he prefers that, or he finds it better, or he likes when everything is predictable. But in the case of quantum mechanics and quantum physics, everything changes. Everything that happens in the world, everything becomes more of a guess, a probability, rather than something that can be a spot-on prediction. Like, I guess in regular classical physics, you guys can determine the acceleration of an object using the forces, or you can predict how far an object will travel when it's thrown using projectile motion and the equations for that. So stuff like this you guys can use to predict exactly where the object will land, or where the result of whatever problem you're solving. In the case of quantum physics and quantum mechanics, everything's completely different. So the only thing you could possibly do is guess or find the probability, and that just basically means everything is by chance. So this is something that really bothered Einstein. He even wrote an article back in, I think it was 1935. He wrote an article regarding how quantum mechanics and quantum physics was not complete, and what had to complete this was, he didn't refer to as quantum entanglement, he referred to, as I explained before, the spooky action from a distance. So Einstein talked a bit about this, and many people and physicists say that he probably knew exactly what quantum physics and mechanics is, and he probably had a better understanding of it than he actually let on, but he could not come to terms with accepting that that's a true thing, due to it all being based on probability rather than reality, or like actually occurring. So that's a little bit about the history of quantum entanglement and what it is. So fun fact regarding black holes. So another article back in 1935 which Einstein published, he didn't say that it was regarding black holes, but he referred to all the characteristics of a black hole and what black holes are. So he basically, at the time, they didn't know what black holes were. Now in modern days, we know exactly what Einstein's talking about. Everything he described in that 1935 article were regarding black holes, and I know this is like, you guys probably thought this was like fantasy and something that wouldn't exist, but he talks about wormholes as well. Of course, he didn't say it was a wormhole. He used a lot of physics or mathematical terms to describe what he was referring to. So what happens is that there are two black holes, and you could form wormholes between the black holes if you were to provide both with enough energy, and then quantum entangle both of these black holes. This would result in this wormhole over here. So this wormhole is what connects the two black holes. So what keeps these black holes connected through the wormhole is actually quantum entanglement. It's a real cool fact I learned through some research I did. Okay, so here I have a few equations. So I'm pretty sure many of you have probably identified which equations these are by now. So these are the first and probably the most significant equations we learned in physics. We initially learned them in kinematics, and use them throughout all of our units. We call these our big five equations. So this is mainly used in what we call classical physics, or physics at a macro level. So the reason I'm showing you guys these equations is to help you guys understand how different quantum physics is from classical or macro level physics. So using these equations, like for example the first one helps us find v2 if we have the remaining three values, and you can rearrange to find other values such as the acceleration or the time that took for the current to occur, or for the first velocity, and so on. So this allows us to predict accurately exactly what would happen. But there's a huge difference between this and quantum physics, which is here we're able to accurately predict exactly what would happen. But when we're looking at quantum physics, if we were to solve for one of these variables, what we would get is the probability of v2 being a or value b. So all we'll be receiving is just the probability, so we won't be given the exact accurate value of what it could be, because on the microscopic or quantum level, everything is by chance. Nothing is predictable. Everything, the only thing we can possibly do is guess on the highest probability of a value occurring and the probabilities of another value occurring, and using that to guess what most likely will happen. So you guys may be wondering, well, basically the microscopic level is just supposed to be a subdivision of like the macro level. Well, this is where quantum physics and like quantum mechanics starts to get a little more I guess complicated, kind of confusing. So the way, as I explained before, how superposition works, as soon as you start measuring the object, it becomes a certain state. Otherwise, it's in a mixture of multiple states, and there's a probability of one or the other state occurring. So what happens is, technically everything that happens is in that probability like state, but what happens is, as soon as we observe, look, measure at something, then it goes from its probable state to the definite state, so the actual state it's in. So this could be a little confusing for you guys. I'll explain more in depth in next few videos, as they'll be going more in depth in what quantum mechanics is and how it works. So this equations, they were supposed to show how different classical and quantum physics are. And it should give you guys a small connection between the two physics. So in both cases, we are predicting or trying to figure out what the possible value of a certain variable or the solution to a certain problem is. But in the case of quantum physics, you only get the probability or the chances of the value being this or that, or this or that occurring. But in the case of classical or macro level physics, what happens is you have a definite value. So I guess, like, for people who don't understand quantum physics, you guys could think of it as quantum physics is a combination of a not definite state and a definite state, while the macro level or classical physics is when an object will take a definite state. So that's probably the easiest way I can think of to explain this to you guys and give you guys a better understanding of what quantum physics is compared to classical or macro level physics. If you guys have any questions, please don't hesitate to put them in the comment section and I'll answer them as soon as possible. And if I find them really mind-boggling or I can't answer them or I feel like I can't, I will do some in-depth research and perhaps create another video that answers that question. So I'm hoping you guys have a pretty good understanding of what quantum entanglement and superposition is by now. So I just want to do a quick recap. So quantum entanglement is basically a mysterious or spooky force or whatever which connects two objects together, and when one object is affected, immediately the entangled pair is also affected by whatever happens to the other pair, as I explained in the heads and tails example. And I talked a little bit about the black hole and how quantum entanglement creates wormholes connecting the two together and resulting in simple transfers from one part of space to another. Of course, that's not possible as of now because you'd be pretty much killed if you tried to go through a black hole. Even light can't escape it, so that's how powerful it is, so it would probably just rip you to shreds. And then finally, I explained the differences between classical physics or macro level physics and quantum physics. So that's about it, guys. I'll see you guys in the next video.